This video will cover the base-promoted alpha halogenation of ketones. First, a note on terminology. A base-promoted reaction is different from a base-catalyzed reaction. Remember that a catalyst is reformed or regenerated and therefore is not used up in the course of the reaction. A base-promoted reaction requires base to occur, but that base is used up and not regenerated. Therefore, we need a full equivalent of base to make the reaction proceed. Let's look at an example of a base-promoted alpha halogenation reaction. In order to simplify our discussion, we will look at this ketone because this ketone only has a single alpha proton. If we treat this ketone with hydroxide ion and a halogen, we will see substitution of a halide for the alpha proton. The mechanism for the formation of this product is base-promoted, meaning that the first step will be a deprotonation. The alpha proton is removed by the base to form the enolate ion. Remember that the enolate ion is stabilized through resonance. The enolate ion is a good nucleophile and can attack the halogen. To form the alpha halogenated product. In this example, there's only a single alpha proton. If there are additional alpha protons present, they will also be substituted in this reaction. Next, let's consider this reactant. This reactant has 2 alpha protons, and in the base-promoted alpha halogenation reaction, both of them will be replaced by halogens. The mechanism for this process is exactly the same as we saw previously. In the first step of the mechanism, hydroxide ion deprotonates the ketone to form the enolate ion. The enolate ion then attacks the halogen to form the monohalogenated product. The alpha carbon is then deprotonated the second time to form the enolate, which then attacks another molecule of halogen to form the dihalogenated product. At this point, the reaction stops because there are no more alpha protons to be removed. The base-promoted alpha halogenation of ketones continues until there are no additional alpha protons that can be replaced. This is because as alpha protons are replaced by halogens, the remaining alpha protons become more acidic. In other words, the ketone alpha protons are less acidic than the monosubstituted ketone alpha protons. We can understand why this is if we look at the conjugate bases of each of these ketones. In other words, the enolate ions. The enolate ion of the monohalogenated ketone is more stable due to the inductive effect. The halogen acts to pull electron density away from the negatively charged carbon, helping to stabilize it. Because this enolate ion is more stable, it is a weaker base, and its conjugate acid is a stronger acid. Therefore, it's impossible to stop the base-promoted alpha halogenation of ketones before all of the alpha protons have been replaced. For example, in this particular molecule, it would be impossible to isolate the monohalogenated ketone. The second step of this reaction, the dihalogenation process, happens more quickly than the monohalogenation, and we can only obtain the dihalogenated ketone product.